Thanks everybody for coming out today after the beautiful weekend that we just had. I was just telling April, I'm pretty sure this is my first time introducing a speaker who was a former PhD student of mine, so a very proud moment for me to do that. But also, very nice because as April or Yun pointed out, sorry, I should use Yun.
It's fine.
I'm so used to calling you April. But as Yun pointed out, she defended her PhD during the pandemic virtually, and so also this is giving her an opportunity now to share her research and even beyond the research that she did here in this sort of proper in-person setting, which is a nice thing to do as well. So just to go all the way back, historically, I think Yun started working with me in 2015, if I'm right, 2014 or 2015.
Yeah.
So 8 years ago now. We basically started off, I think, by studying the role of clouds in the Earth radiation budget. Over the years, I think we did a lot of work together working on the role of both clouds and aerosols, and actually the different types of clouds and aerosols in the climate system. But over the time that Yun was doing her PhD, she also developed interest in a lot of interdisciplinary areas. I know she talked a lot with Brad Pierce about air quality and aerosols, and also got interested a little bit in sort of the implication of clouds for energy production. And so it was a very natural fit for her to transition into the Nelson Institute, and so she actually did her PhD in AOS as her sort of home department, but in the what's it called, Environmental and Resources PhD program within the Nelson Institute. At the same time, she was able to do the Earth Analysis and Policy Certificate, and I think it's basically a lot of the exposure that she got to other fields that has pretty much shaped what she's doing now, which is very interdisciplinary and very much sort of applications of what we do in atmospheric and oceanic sciences. So she now is a Climate and Health Postdoctoral Research Fellow in the Emory Rollins School of Public Health. And she's working a lot in the intersection here between air quality, public health, and environmental justice. Very, like I said, interesting and important topics, and also just, I think, like I said, a kind of a testament to the exposure that you got in the Nelson Institute of all these different areas and fields. So it's very nice to see the success that you've had from there. So just as a sort of brief summary of the main topics that you're working on, and I think you'll talk about the last one here. So you're studying the environmental risk factors faced by underserved communities within the U.S., the impact of aerosols on climate from satellite data, still sort of an underlying theme, and then trying to do some environmental exposure modeling using machine learning. I think that's what you're going to be talking a little bit about today. So anyway, without any more sort of delay, I'd like to introduce Yun Hang, my former PhD student, to give her seminar on what she's working on nowadays.
Yes. First, good afternoon, everyone. I'm a postdoc studying the intersection of atmospheric science and public health at Emory University. And before Emory, I was student with Tristan. And previously, my work is about using stellar remote sensing to study different cloud types and their influence on Earth's energy budget. And during COVID-19, inspired by my father, he is a pulmonary doctor actually. He was fighting the virus at the front line. So about two years ago, I was determined to pursue a career path to apply atmospheric science to health issues. So at that time, I emailed to a professor in the Emory University, and he replied me. So I was fortunately selected by the Emory Rollins School of Public Health as the very first climate and health postdoctoral research fellow. So I'm very unique in that place. I'm the only person there who have a climate science background. And now my research is still using the stellar remote sensing, but more related to different aerosol types and their impact on human health. This is a previous group photo with Tristan's group. And this is a new photo with my current group in Emory. We're still doing a lot about remote sensing. So for example, like today I'm going to share my recent work. on the application of satellite data in PM2.5 constituents modeling. Specifically, I will focus on particulate nitrate. Nitrate is one type of PM2.5 constituents. For this study, I will show my work about how to predict the historical pollution level of nitrate in China and evaluate its long-term health risk. Okay, next. So my presentation will cover 3 topics. First, I will give a brief introduction of PM2.5 constituents and the current situation of particulate nitrate air pollution in China. And second, I will introduce a satellite remote sensing-based approach to model historical PM2.5 constituents concentrations. I will take nitrate as an example to illustrate a general methodology. And last, based on the nitrate exposure model, I will assess the long-term mortality burden attributable to nitrate in China. And actually, this is the very first estimate at the national level. Because like before, the long-term exposure estimate of nitrate was not explicit. So, okay, let me start from introducing PM2.5. I believe many of you are very familiar with this figure if you study PM2.5. The PM stands for particulate matter, which means a mixture of solid particles or liquid droplets found in the air, for example, like dust, pollen, or mold. And PM2.5 refers to the tiny particles with diameters of 2.5 micrometer and smaller. And this figure shows that the PM2.5 is about like 30 times smaller than human hair. It's very, very tiny. So these PM2.5 particles can actually travel deeply into humans' respiratory systems, reaching the lungs, and numerous scientific studies have linked PM2.5 to a variety of health problems, such as the asthma, lung cancer, and heart disease. Yeah, there's a figure about the PM2.5 toxicity. And in China, the PM2.5 air pollution was very severe, and it has been estimated that the long-term PM2.5 exposures have accounted for 30.8 million adult premature deaths during the year from 2000 to 2016. And these 2 photos captured extreme air pollution levels in Shanghai and Beijing, the 2 famous mega cities in China, and in the winter of 2013. And as you can see from the figures, it's very hard to tell the skyline of these 2 cities. And considering the health effects of air pollution, the Chinese government immediately implemented the toughest ever air policy, APPCAP, short for the Air Pollution Prevention and Control Action Plan, in the year of 2013. And as a result, the air quality in China significantly improved after 2013. And this map shows that the annual mean PM2.5 concentrations have substantially decreased from 2013 to 2017, especially in North China, where the capital Beijing locates. The reduction is about around like 55 microgram per cubic meter. That's such a large reduction. However, a large reduction of total PM2.5 concentrations does not mean the toxicity of the air reduced accordingly. Because PM2.5 is a mixture of many constituents, such as the organic carbon, sea salt, black carbon, sulfate, and nitrate. And the toxicity of individual constituents are very different. For example, the particulate nitrate, which is mainly generated from traffic emissions, coal combustions and biomass burning is likely to have an elevated toxicity. This chart shows the association of PM2.5 constituents and sources with ischemic heart disease mortality. And nitrate was found to have the highest hazard ratio among these particles. The hazard ratio is a term about health risk. So nitrate might have elevated toxicity. And considering the different toxicity of PM2.5 constituents and the large reduction in total PM2.5 concentration in China, researchers are curious about the change of PM2.5 constituents. And recently, several studies have reported the temporal variations of PM2.5 constituents at limited ground monitoring sites. And this chart shows the concentration of major constituents in PM2.5 observed in Beijing during winter from representative particles. The top 3 constituents with the highest concentrations were nitrate, sulfate, and ammonia, colored in blue, red, and yellow, respectively. And it is found that the sulfate concentration contributed to the most PM2.5 masses before 2015, ranged from around 16 to 25.5 microgram per cubic meter. But since 2015, nitrate concentration has exceeded sulfate as a dominant constituent and ranged from around 23 to 29 microgram per cubic meter. And note that in the year of 2017, although the total PM2.5 mass substantially decreased, the nitrate concentration was still very high. So, together with a possible elevated toxicity of particulate nitrate and its high concentration, it is needed to study the health impact of long-term nitrate exposure in China. Okay. So, the research objectives of this presentation are improving our understanding of PM2.5 constituents and their health effects, and specifically investigating the health impact of long-term nitrate exposure in China. Therefore, we can further improve air quality to promote public health in China and globally. Okay. So to study the health effect of the nitrate in China, the first step should be estimate the national level long-term nitrate exposure. However, the ground monitoring network of PM2.5 constituents is not existed in China. That causes a large barrier. Unfortunately, satellite-based observations can help estimate PM2.5 constituents. For example, the multi-angle imaging spectroradiometer, short for MISR, is an instrument aboard NASA's Terra satellite that can measure upwelling solar radiance in 4 spectral bands and at 9 view angles over a 360 kilometers swath. And this is an image acquired by MISR's forward viewing camera that captures smoke over Southern California on July 23rd, 2016. And from this figure, you can see the location of the smoke colored in white, but you don't know the concentration of the smoke. And recall that the MISR also has 9 cameras that can monitor the Earth at the 9 view angles. Therefore, it can capture aerosol optical depths, AOD, of different aerosol types. And the aerosol refers to solid or liquid particles in the air, such as urban haze, smoke, like dust, sea salt, and AOD is a quantitative measure of aerosol abundance in an atmosphere. So the figure on your right-hand side is a map of AOD retrieved from miser observations. The different colors represent the variation of the smoke concentration. For example, the color of deep blue and dark indicate the region that had a severe smoke pollution. Okay, so besides the total AOD, the miser can provide unit information on fractional AOD, which means it can split the total AOD into different components. In this way, the fractional AOD can provide information on aerosol microphysical properties, such as the particle shape, size distribution, reflection property, and scale height. In general, the miser can provide observations of 74 aerosol mixtures. And based on mixtures, we can calculate 8 types of fractional AOD components that can be used to identify nitrate from other types of aerosol. So here's some information about the aerosol mixtures from miser and fractional AODs, and details about the calculation can be found in previous papers. So considering the physical characters of nitrate, we calculated a series of non-spherical and non-absorption fractional AODs by miser data to isolate particulate nitrate from other aerosol types. But however, the temporal resolution of miser aerosol data is low because it's on board a polar orbiting satellite. So the global coverage is of every 9 days. Yeah. Okay, that's miser fractional AOD. So back to the question, to evaluate the exposure of nitrate in China, an emergent solution is using machine learning model incorporating ground measurements and satellite data to predict the full coverage of nitrate concentration. And in this study, we chose the random forest algorithm as the machine learning model because it allows a flexible number of predictors to estimate the relationships between the nitrate and various impact factors. And the final prediction model is determined by comparing the results of different settings of predictors. So based on the method, we built a long-term nitrate exposure model that covers the entire China during 2005 to 2018 with a spatial resolution of 10 kilometers. And we focused on 3 the most populated city clusters in China, including the Beijing, Tianjin, Hebei region in the north of China, the Yangtze River Delta in the east of China, and the Pearl River Delta in the south, also the Chenyu region in the west, to investigate the influence of air quality policies. And this map shows that the ground monitoring sites of PM2.5 constituents are sparsely distributed in China, but cover the most populated regions. So it's not too bad. Okay. And our model inputs include the annual mean miser fractional AOD and available ground daily observational records of nitrate concentrations, also daily meteorological conditions from geosphere analysis, daily atmospheric compositions from chemistry analysis, and monthly level emission inventories, also monthly level NEVI, and we also have 1-year data of the lowlands in China. From this chart, we can see the modeling data of nitrate, PM2.5, NO2, humidity, and observational data on miser fractional AOD, number 19, ranked the top 5 significant predictors. Note that although the temporal resolution of miser is low, it's only at annual level, it still contributes a lot to this machine learning model. You will see a lot of data from miser. So this model is heavily miser-based. And this chart shows that our model performance is of high accuracy. For example, at monthly level, the linear regression between the predictions and observations produce a slope of 1.09, close to unity, and intercept of 1.16, close to 0. And the out-of-band cross-validation R-square between the observations and predictions is high. It's about like 0.88, indicating a minor prediction bias. But the spatial CV of this model is not that good, but it's fine because as I showed in previous slides, the ground monitoring sites are not evenly distributed in China. So the spatial cross-validation is not that well, but we still can use it. So based on the newly developed nitrate model, we are able to predict the temporal trend of nitrate in China from 2005 to 2018. And these figures compares observations and predictions of nitrate at different monitoring sites in China, showing as red and black lines respectively. So before 2013, only a few monitoring sites documented nitrate levels in China, such as the one in Xi'an, located in the northwest China. And the nitrate level of Xi'an was observed high in winter and low in summer. Our model successfully predicts this seasonal cycle and the extreme values over the seasons. And the figure B compares the model predictions with high quality observations in Pingtong, a supersite in Taiwan. And it is showing that our model can accurately simulate the decreasing nitrate trend from 2006 to 2010. And then, starting from 2013, the ground monitoring sites of nitrate became more available and appear in many other regions in China. We present the comparison results of 4 sites representing different geographical locations in China, including Harbin in the northeast of China, Beijing in the north, Chengdu in the west, and Shanghai in the east. We found that the nitrate level was stable after 2013, or even became higher in 2017 and 2018, despite the total PM2.5 has substantially decreased after the implementation of the APPCAP, the toughest ever air policy. And interestingly, a minimum of nitrates was observed at the Chengdu site in 2016, and that's likely related to abnormal meteorological conditions. Okay. And further, based on the exposure model, we estimated the temporal trend of nitrate in China during this study. The red line shows the annual mean nitrate level in China, the national mean trend. Before 2013, the nitrate peaked around 9 microgram per cubic meter in 2006 and decreased to 8.5 microgram per cubic meter in 2012. And this reduction was likely due to the 11th 5-year plan in China that has effectively reduced emission from industry facilities. And in addition, two vehicle NOx emission standards was established during this time. during the National 3 standard implemented in 2007 and National 4 standard implemented in 2011. These two emission standards successfully controlled the on-road vehicle emissions. And after 2013, the national level of nitrate decreased from approximately 9 microgram per cubic meter in 2013 to around 7.5 microgram per cubic meter in 2018. And this trend was contributed by the 12th five-year plan and the APDCAP, accelerate the denitrification in industrial facilities. And the minimum nitrate level appeared in 2016 at around 7.4 microgram per cubic meter, was likely influenced by favorable meteorological conditions that suppressed the nitrate formation. So compared to other PM2.5 constituents, such as sulfate, nitrate is much more sensitive to temperature. For example, the thermodynamic formation of ammonium nitrate favors low temperatures. And in the winter of 2013, actually was much warmer than normal. That may contribute to the low nitrate level in that year. And overall, the national nitrate level was relatively stable actually, with a range of less than 2 micrograms per cubic meter during the whole study period, and even slightly increased in recent years. And that is consistent with research findings from other studies. And the possible reason is the rapid growing vehicle population increased the nitrate generated from traffic emissions, offsetting the reduced nitrate from industry emissions. And the 4 black lines represent the nitrate level in 4 city clusters, and recently the BTH, Beijing, Tianjin, Hebei region, was the most polluted cluster during the entire study period. That's because, probably because the BTH not only have the numerous coal-fired power plants, but also has a large number of vehicles, which are the major sources of generating NOx, which is a precursor of nitrates. Okay. So we then use the model to predict the spatial variations in nitrate in China. And this map shows the annual average nitrate concentration during the study period. We found that the nitrate was especially high over 3 types of regions. First, the nitrate was high over major traffic corridors. For example, the nitrate level over the south part of the Shanxi province, was about around 5 microgram per cubic meter colored in white, but increased to around 10 microgram per cubic meter along the traffic corridors, colored in orange. This is actually the upper section of the Beijing-Kunming Expressway, and this finding was not reported in previous studies. The nitrate was also high at regions with many coal-fired power plants and extensive industry facilities. Besides that, nitrate was also high over cities with high vehicle usage and dense road networks, such as the 2 cities here, Chengdu and Chongqing, where the vehicle usage were the highest among the cities in China. average nitrate in China. The highest level was observed in winter, mainly because China's central heating system is coal burning based, making coal combustion the dominant source of nitrate during the heating season. And the populous regions like in North China with central heating experience nitrate at about 20 microgram per cubic meter, colored in dark red in this figure. And in addition to anthropogenic factors, meteorological conditions such as low temperature also raise the nitrate level in winter. And the nitrate of spring and autumn was similar, except the nitrate was high in autumn over North China. This is because the central heating started in the region in around like late October or early November. And the lowest nitrate level was observed in summer months with a concentration generally under 5 microgram per cubic meter, colored in blue in this map, and across China, but increased to around like 10 or 8 to 10 microgram per cubic meter over province with many power plants and along traffic corridors, and confirming again the industry and vehicle emissions make significant contributions to nitrate pollution in China. Okay. So further, with a newly developed nitrate exposure model, for the first time, we estimated the mortality burden of long-term nitrate exposure in China. We utilized the pooled relative risk of nitrates reported by a systematic review paper. Their meta-analysis summarized the health impact from nitrate from 3 cohort studies, including estimates from the Medicare cohort, California teacher study conducted in the United States, and also a cohort of 2.4 million people in Canada. So with that paper, we calculated the mortality burden based on the pooled relative risk of nitrate. We first calculated the relative risk of nitrate over each gray cell of each year with the model estimate, exposure estimate. Then we calculate the population attributable fraction of each gray cell I in each year. The population attributable fraction is under that level, like the nitrate is not toxic, is like not toxic, and that was calculated as the minimum of the nitrate exposure in the model. And finally, we calculate the absolute number of adult deaths caused at premature level. And this figure summarizes the mortality burden attributable to long-term nitrate exposure in China. The figure 8 compares the annual mean premature death rate attributable to nitrate in each province of China in the first year, 2005, and last year, 2018, of the study period, and the year APPCAP was implemented, the year of 2013. And it is found that the death rate of BPH, Henan and Shandong province, was more than twice the national average, at about 20 per 10,000 persons. And the low death rate was observed in Tibet, Yunnan, Hainan, and Taiwan, where the rates were below 5 per 10,000 persons. And the figure B shows the national mean annual nitrate concentration and its corresponding premature death number during the study period. We found that the premature death number decreased from 0.77 million to around 0.65 million from 2013 to 2016, but increased to around 0.68 million in 2008, confirming that the China's clean air actions was successful, but may need more effort to reduce nitrate air pollution. Yeah.
So how does this relate to, I guess, the death rates from other pollutants?
Yeah, in the paper, we compare the death rate of nitrate to the total PM 2.5. It accounts about 1/3.
Oh, wow.
Yeah, this is the very first nitrate model, and I also developed model for other PM 2.5 constituents. So we'll compare the mortality burden later, compare with other PM 2.5 constituents, right? Their mortality burden.
Okay.
Yeah, and this is the national average estimate, the general idea. Yeah, and the nitrate accounts that much is because the concentration is high now. Yeah, the toxicity is still known, is unknown because there's no study in this data. So this is the very first step.
Okay.
Yeah.
So that toxicity, does that enter in that beta factor then?
Yeah, beta factor.
Okay.
Yeah. And also we consider the baseline mortality in China.
I see.
Yeah.
I see.
Okay. And in summary, this study brings 3 key messages. The first, it shows a high performance exposure model that can be developed to predict the nitrate concentration in China based on machine learning techniques incorporating limited or available ground measurements, satellite observations from MISR, and other supporting information such as data from reanalysis. And second, the nitrate level of China was high over regions with many coal-fired power plants and extensive industrial facilities, or large civilian vehicle fleets, as well as cities with dense road networks. The last message is the mortality burden attributable to long-term nitrate exposure still remain very heavy in China. So more efforts are needed to reduce nitrate pollution in China. And our study is not perfect. We have a few limitations. The first limitation is we don't have a lot of ground data to train the random forest model. So in the future, we hope to include more data when they're available to improve the model's performance, its stability, and accuracy. And second, the MISR swath is narrow and leads to limited spatial coverage. In the future, we'll use the gut filling approach to fill missing AODs retrieves to improve the model's spatial coverage. So I don't know if you noticed on previous maps, there is no data over Tibet someplace because the MISR is not that good with the temporal resolution is not that good. And the last is the relative risk of nitrate was pulled from a cohort study conducted in the United States. 2 of them conducted in the US, and 1 of them conducted in California, and they're not conducted in China. So in the future, we hope to generate a national specific health risk assessment when a cohort study of nitrate in China will be available. And in the end, I want to share that I also already mentioned, we have already developed other exposure models of PM 2.0 constituents, such as sulfate and black carbon, and I will introduce more at the coming AGU for meeting 2022. So feel free to stop my session. If you come to AGU this year, I'm happy to introduce and discuss more with you. Yeah, and that's the end.
Any other questions? John?
I guess I have a question, Yoon. What about, there seems to be interannual variability in the winter in North China. Beijing is cold some years when the Siberian Mongolian high has this eastward extension that people have written about. Is that something that within a given cold season even varies? So can it be bad in in December, January, and not so bad in February, March? Does anybody know about that?
You mean for a specific year or general?
Yeah, for a specific year. I mean, is there within a winter season, is there enough variability to merit attention to look at individual months?
You mean the nitrate
Yeah,
concentration?
and related to, the cold or lack thereof.
I would say there will be a difference. And as I introduced, the nitrates, different like other constituents, is very sensitive to temperature. And it favors the high temperature. So I would say if the temperature is high, we can expect a lower level of nitrate. But at the same time, the nitrate is also sensitive to humidity. And also, like in Beijing, there are a lot of mountains around, and the winds also play a major role in the concentration. So
Okay.
I won't say it will directly contribute at different levels of nitrate, but will definitely influence about the
The
concentration.
production, okay.
Yeah.
All right.
I believe a lot of studies reported the observation results over Beijing because that's the capital. Yeah.
Yeah.
So if you're interested, you can take some.
Okay,
Yeah.
thanks.
Yeah. Yeah.
So I have a question about the model
Yeah.
from somebody who does absolutely no machine learning. So please correct me if my question makes no sense. So whenever you did, well, I guess first, what did you use for your training data?
With what?
The training data, like what time range did you use for your training data?
Yeah. Our training data range from 2005 to 2018, cover the entire period.
Okay.
But before 2013, very limited data existed in China. I give two examples. Actually, that's the only two, not only two. In mainland China, only in Xi'an city has the ground monitoring network, ground monitoring data before 2017. Probably some data in Beijing, but very few data before 2013. Most data come from in Taiwan, because the Taiwan monitoring system different from mainland China. But start from 2013, we have a lot of data from China CDC. Yeah, so
So for your forecasts, then, how do you do that? Like I'm thinking in terms of like what you would do with like multiple linear regression or something like that to compute your weights. Do you just like to do your hindcast essentially? Do you just like take out a year and then retrain the model and then forecast the year, and then you do that with every single year?
we use all of observational data to train the random forest model. So we use the ground data to learn the relationship between the nitrate concentration, for example, and the miser data. Use the random forest to learn the relationship. But that's only based on the ground data, so it's point-based. So we learn the relationship from the point data. But once we know the relationship, we can predict other places that have the AOD from the miser.
Okay, so the goal is not to predict where you have data because you're using the data for that
To
time
learn
period,
that.
but rather to predict the regions that don't have any data.
Yes,
right?
exactly. So you learn the relationship first, then predict to get the full map. Yeah.
I guess maybe what you're getting at is often they'll exclude one of those monitors from the training set
Mhm.
and see whether you can predict one that wasn't in the training set.
Yeah, we did that.
You did that.
Yeah,
Okay.
so in the cross-validation chart.
But then I have some other questions too.
Okay.
You go with that first.
Yeah.
That's good. So you did cross-validation where you
Yeah.
excluded some and you still got
Yeah.
good predictions.
So we use like 2/3 of the ground data to train the model,
Right.
and the remaining to validate the model. Yeah.
So you brought the figure that showed which variable had the highest impact. You brought CAM's chemical analysis in, and I think you were using that, for example, for NO2, nitric acid, and O. Have you thought about using, for example, tropomi NO2 retrievals so that you'd have a satellite that was providing that instead of a model?
But tropomi does not have data for
Oh,
2005.
right, but maybe, that's right.
Yeah,
So
so
you could
our
only use
study
it later
here-
on.
Yeah, we thought about that.
Or OMI,
Only, probably
yeah.
only.
It might be interesting to see.
Mhm.
And the reason I ask that is Shobha Kandagut and her group,
Mhm.
they've looked at, this is my second question, they've looked at how PM 2.5 as a whole changed during COVID, and they actually used tropomi NO2 to identify the anthropogenic part of the aerosol optical depth. And so I'm wondering, with COVID,
Mm.
you've got significant reductions in industrial activity and automobile traffic. Have you looked at extending this and seeing how well your model captures COVID with the reductions, or even retraining the whole data set around this COVID period where you've got this really significant reduction probably in nitrates?
Yeah.
But on the sad part is you also have this significant increase in mortality because of COVID. I'm just wondering how much did you, by improving air quality, did you kind of reduce nitrate-related
Yeah.
mortality?
The limitation is we don't have ground data after 2018.
Okay.
So that's the reason why our model was stopped at
Okay.
that year.
Okay.
You know, the ground data is not open in China.
I see.
So in the past, like the first year during my postdoc, during daytime, I tried to play this model. During nighttime, I collaborate with Chinese government, CDC, to try to get as much as data from them to train the model. So yeah, that's the story. So that's the reason why we stopped after 2018.
Okay.
Yeah, but we're really interested in the COVID period. Mhm. Yes, please. Yeah.
You go first and then we'll go back.
What's the relationship between surface PM 2.5 levels and AOD? Like, is it a 1-to-1 almost? Because an AOD is a column measurement, right?
Well, AOD is a column. It will influence by a lot of things. For example, the cloud cover. So it's different, but it has some relationships. For example, if the concentration of the PM 2.5 is very high, definitely there less light will penetrate the atmosphere layer. Right? So they have relationships, but not exactly the proportion to. Yes.
I know Brad stole half of my question, but the other half is we talked a little bit about policy related to your work. So it seems these mortality rates are really high, and when we look at these health indices around the world, they're mostly focused on PM 2.5 or ozone. Do you think that there should be another index for nitrates as well?
Good question. There is no index for nitrate at this point, but some health experts, like in the US, suggest to have another index for the elemental carbon, because that one is of also elevated toxicity. Yeah. So not for nitrate, or for elemental carbon. Suggest that. Mhm. Yes, please.
Is all your training data in populous area or high population cities?
Yeah, most of the data was collected in populated regions, but around 1/3 of them over the rural regions as well.
So does the model do well in less populated rural area?
As I showing before, the spatial validation is not that ideal. because the sites are not evenly distributed in urban and rural areas, but not too bad. So this model is the first step. In the future, we definitely can improve more if we have more data from the rural regions. Yes, please.
Along the same lines, does your model take into account shifts in population density over time in regards to how that might increase the nitrates within a certain region?
Sorry, I cannot hear you clearly.
I'm wondering if your model takes into account changing population density.
Yeah, I tested population density in the model. It performed not, it's not good, so I removed it. Yeah, we tested that. So when we're developing the model, we always try probably 100 of times, try different predictors, different data. And then once we have results, we'll compare with the ground monitoring sites results, was not used in developing the model. So we tried population, but it works not that good.
The population was included then later when you calculate the death, the fractional.
Yeah, we include that.
Yeah.
Yes,
Yeah, I
of
see,
course.
I see.
Yeah.
One more question.
So the humidity and the temperature variation, can you just, you said that when it's colder, you tend to produce more of the nitrate, or vice versa?
More.
More nitrate when it's colder.
Yeah.
Okay, and then the humidity, how does that impact?
Humidity probably high, more.
Okay.
Yeah.
So
It
cold.
increases the size of the aerosols.
Mm-hmm.
Okay.
Humidification,
Okay.
FFRH.
Okay. Does that affect the
Affects the, for sure.
it affects the aerosolical depth, but does it affect the production of nitrate, I guess? Okay. Interesting. I was interested in the seasonal maps that you have where, I mean, there's so much more in the wintertime than
Yeah.
in the summertime, and that could be emissions, but it could also be production. And so I'm curious.
The central heating in China plays a large role
Yeah.
in the nitrate formation.
Got it. Nice. And it's a really interesting, I mean, it really shows the potential of using satellite observations in this, in public health and the cool things you can do there. So I just want to, just a side note, it's a really interesting what you did there.
Well, this result shows the model developed by Miser data. Actually, Miser is kind of an old mission, for more than 20 years. And there is a new mission coming up called the Meyer. That mission is the first NASA mission about public health. That one, is developed to study the PM 2.5 constituents. So back to your question about probably we have other index in the future for different PM 2.5 constituents. We'll know that answer once we have the Meyer mission collect more data about different aerosol types. At that time, we'll know. So probably after 10 years or 20 years, we'll know the answer. Yeah.
All right, join me in thanking Yoon again. And when do you leave? Are you're finished at the end of today, or do you have any time to-
6:59
Oh.
p.m.
Okay, so unfortunately no more time to follow up, but follow up by email if
Yeah,
you have any other questions.
Oh, I'll take photo.